Now let's consider integrals that involve inverse trig functions. But before we think about integration, let's recall the derivatives of inverse trig functions. So the derivative of the inverse sine of x over a we found to be 1 over the square root of a squared minus x squared. We also know that the derivative of the inverse tangent of x over a is equal to the fraction 1 over the quantity a squared plus x squared. And we'll also look at the derivative of the inverse secant of x over a, which is 1 over the absolute value of x times the square root of x squared minus a squared. These are our three main inverse trig functions that we'll be dealing with. Now we can take these derivative rules and rewrite them as integration rules. So rewriting these as integrals, we're going to integrate our right-hand sides. So we'll write the integral of 1 over the square root of a squared minus x squared dx for our top differentiation rule. We'll write the integral of 1 over the quantity a squared plus x squared dx. And then for our last one, we're going to write the integral of 1 over the quantity x times the square root of x squared minus a squared dx. So for a time being, we'll leave off the absolute value, and we'll see that it will reappear on the other side. Using our antiderivative property, we know that the top integral is simply going to be the inverse sine of x over a plus a constant because it's an indefinite integral. Our next integral is the inverse tangent of x over a plus a constant. And our last integral is going to be the inverse secant of the absolute value of x over a plus a constant. So we see that the absolute value shifts over to the answer side of our integral formula, just like it's in the answer side of our derivative formula. So what we're looking for when we're trying to use inverse trig functions in integration is integrals that have one of these three forms. So they're a little bit complicated, but hopefully we'll be able to recognize them. Let's evaluate a couple integrals. First, let's evaluate the integral of 2 divided by t times the square root of t squared minus 9 dt. So if we come and look at our three forms, we are most clearly matching the bottom form. We just have a different variable of integration, and then we just need to sort out our constant. So it's relatively straightforward to see that our x in the formula will become t for our particular integral, and that a squared is equal to 9 in our new integral, so that means that a is equal to 3. So, taking into account the fact that we have a factor of 2 here on the top that is not anywhere in our formula, we will write that out, and then we will apply our transformation x equals t and a equals 3 to our integral to write our answer as inverse secant of the absolute value of t over 3 plus a constant. Now, some of our integrals will look a little bit more uncertain in terms of our substitution. So if I look at the integral of 3x divided by 4 plus x to the 4th dx, it is not immediately obvious that it fits one of these three forms. However, if I rewrite my integral just a little bit, first I'll pull out a factor of 3, and then in the denominator, I'm going to write the x to the 4th as x squared squared. So now if I think of u substitution, where my u is equal to x squared, I know how to take a du, take the derivative of u, I get du is equal to 2x dx. Now, applying my u substitution technique first to this inverse trig integral problem, I end up with the integral of 3. Now, I don't exactly have 2x dx, I have x dx. So I will replace the x dx with the du over 2, and the rest of my fraction becomes 1 over 4 plus u squared. So the x dx becomes my du over 2. Factoring out that 2, I get a 3/2, and I'm now in the correct form to have a inverse tangent function as an answer. So u will be exactly x, and 4 is a squared, so a is equal to 2. Substituting those values in, I get the inverse tangent of u over 2, and then plus my constant of integration. Now, because I did a substitution, an actual u substitution here, I need to transform back into my original variable. Notice I started in x, I should end in x. So this gives me the answer 3/2 inverse tangent of x squared over 2, since u is x squared, plus c.